Hi folks, and welcome back to Physics with Captain Rod. I'm making this to be kind of an introductory video into the topic of projectile motion. So let me chat about what we're looking at here. We got young Susie here, who's a accomplished archer. And we're going to imagine she's standing on this hillside and she fires her bow 30 degrees with the horizontal. Now, just to make up a value here, let's say that that bow will fire an arrow with an initial velocity of 100 meters per second. Now, that's a pretty fast bow. It is very doubtful that Susie could draw a bow back that would fire an arrow at that speed, but you know, it's conceivably possible. I just want to pick a nice easy number for the sake of this example. And we're going to imagine here that she fires that arrow in a direction 30 degrees from the horizontal. Now, it's very important that we distinguish the difference between these two pictures. Here is the arrow before she fires it. This is intended to be a picture of the arrow the instant after it's fired. So you got to imagine, you know, this string is now vertical, basically, arrow's on its way. This video now has nothing to do with Susie, really. It's all about this arrow. What is this arrow going to do fired at 100 meters per second, 30 degrees from the horizontal? Now, in just kind of a general sense, most people probably have an idea of what's going to happen here. You know, this arrow is going to fly through the air and do something like this. That's what its path is going to look like. And what we want to be able to do ultimately is write equations that describe where this arrow is and what its velocity is at all points in time here. So here's how we do that. The beginning of this is we're going to take this arrow's velocity vector, and I'm going to go ahead and draw this in blue here. So I'm going to put a vector on for the velocity of the arrow. So this blue vector is representing this, 100 meters per second, 30 degrees with the horizontal. I'm going to go ahead and just call that v sub o. Now, vectors can be broken down into components. So what we're going to do is we're going to take this blue vector and we're going to draw it in component form here. It has an x component to the right and a y component up. I would normally call this something like v sub o x direction, v sub o y direction. An important fact of life here is this, that if you ignore air drag, the only force on this arrow is the gravitational force. You know, so here's kind of a picture of the arrow here. At this point in my physics class, I don't think we've even talked about what are called free body diagrams, but for now I'll just say this. All right, the gravitational force is a force that acts down on the arrow. It's equal to its weight. I'll just call it force of gravity here. And if we ignore air drag, which is a reasonable thing to do for an arrow, especially at relatively low speed, then that's the only force on it, right? And what you'll find is that when you look at these velocity components, this one is going to change because of this force. This one is not. This one will stay constant. So I'll make other videos, perhaps doing experiments that demonstrate that. For now, for this video, I'm just going to ask that everybody take my word for this, that this will change due to the effects of gravity. This one won't. Now, this is a 30-degree angle in this example. In another example, we'll just call it theta. The x component of this velocity vector is adjacent to the 30 degrees, so it's going to equal v sub o cosine theta in general. In this example, that would be 100 meters per second times the cosine of 30 degrees, which is 86.6. I'll just say, let's just say approximately 86 meters per second and move on. That'll be good enough for this example. This vector component is opposite the 30 degrees, so it's going to equal v sub o sine theta in general. In this example, that's 100 meters per second times the sine of 30 degrees, which is 50 meters per second. So at the instant shown, what this means is that this arrow is moving to the right at 86 meters per second and moving upward at 50 meters per second. Now let me go through some different potential cases here. Had this velocity vector been purely to the right, like had she fired the arrow horizontally at 100 meters per second, then the initial velocity x direction would be 100 meters per second. The initial velocity y direction would be 0. Had she fired it down at an angle, 30 degrees at the horizontal, then the initial velocity x direction would be the same as this, 86 meters per second. The initial velocity y direction would be the same as this, 50 meters per second. However, this is down. If we're calling up positive, we would assign a minus sign to it. Had she fired the arrow straight up in the air, right, and again, these are velocity vectors, this was not intended to be the arrow, so this represents the 100 meters per second, here the 100 meters per second. Had she fired it straight up in the air, the initial velocity y direction would be 100 meters per second. Initial velocity x direction would be 0. So the first step in any projectile motion problem is to break the velocity vector into horizontal and vertical components. Now, if you know a velocity and an angle, you can get numbers. If something is unknown, for example, maybe we know the angle but an unknown velocity, you still have to proceed the same way. So what you would do is, you would just leave this v sub o times the cosine of some number. If the v sub o was known and the 30 degrees, if the v sub o was known and the angle, I'm sorry, if the v sub o was unknown and the angle was known, you would just put this v sub o cosine of whatever angle. And again, likewise for the angle. If this is a known value and this is unknown, you would put your number here and cosine theta. You just leave it a generic theta. Same thing here. So anyway, you have to do this step here and here. If you have a pair of numbers, you can get numerical values. If you don't, you just leave it v sub o cosine theta and move on. And again, v sub o sine theta and move on. All right. Now when I say move on, let's talk about what does that look like. I need a little room here. All right, so these are analyzed the same way all motion problems are graphically here. We have two different directions to think about, though. We have the x direction and the y direction. So what we do is we look at them independently, x, y. And I always start with the velocity graphs. I'm just going to do quick sketches here and talk about them, because again, this is just supposed to be an introductory video. So velocity graph, x direction. You look at your velocity vector, you look at the x component. In this example, it's 86 meters per second. So I would come up to 86 meters per second. And now I'm going to sketch the rest of the graph. And again, the key feature here is that a second later, maybe the arrow's over here, but the 86 meters per second is still good. Second later, 86 meters per second is still good. So what we're going to get is a horizontal line out to any time t. That'll be true until the arrow runs into something such as the ground. If we have a numerical value, we can go ahead and put it here. If we don't, you can just put v sub o cosine theta and move on, but it's still constant. Then we would graph our position graph. And remember how we get from here to here. They're related by area. This area right here gives us our change in position. So delta x is going to equal this area, 86t. I'll put NCU for note consistent units. Now, if we don't have a value here, we have like v sub o cosine 30, or maybe we have 100 cosine theta, you still do it the same way. Instead of 86, you would put the v sub o cosine 30 and then times t and so forth and keep moving. Now, if we put the coordinate system origin here, this delta x would just be x, because x initial would be 0. Linear graph, plot it out to any time t. So now, tell me an x, I'll tell you a t. Tell me a t, I'll tell you an x. Let's talk about the y direction. Now, in these projectile problems, this stuff is almost always going to look exactly the same, really. The y direction can vary slightly, but not a ton. All right, so velocity against time. In this example, initial velocity y direction was positive 50 meters per second. So we come up here to 50 meters per second. At t equals 0, there's our velocity. Now, Due to gravitational acceleration, a second later, this is going to be roughly 40 meters per second. And a second after that, it's going to be about 30 meters per second, because remember, gravitational acceleration is down at a numerical value of 9.8 meters per second. I like to approximate this to 10 for just, these types of discussions. So again, what that means is this 50 meters per second, right? After a second, it's going to be a 40, and after that, a 30, and after that, a 20, and so forth. So this graph is going to be linear, and it's going to decrease like this. This 0 here occurs when the arrow is at the highest point in its trajectory. Right at that instant, the velocity in the y direction is 0. Then remember, the arrow starts coming back down, and what that means is the y component of the velocity vector is now negative. That's why we're down here on the graph. The only thing that can vary in these problems, right? Imagine that Susie here fired the arrow purely horizontally. Right? Well, then the initial velocity would be 0, and this would start here and have the same shape. Or perhaps she fired it down at some sort of angle, maybe 30 degrees clockwise from the x-axis. And then the initial velocity vector would be minus 50 in the y direction, so this would start here and look like this. So this graph, the only variations are sometimes it'll start here, but it'll slope down like this with a slope of negative 9.8. Sometimes it'll start here, but the shape will be the same. Sometimes it'll start here and look like this, depending on initial velocity, positive, 0, or negative. The equation for this line, I've got lots of videos on how to find these equations, so I'm not going to do that here. It's going to be v equals negative 9.8t plus 50. You can get that from area under the acceleration graph, or from the fact that this is a linear function with an acceleration of negative 9.8 meter per second and an intercept of 50. Your graph for y against t. If I put a coordinate system origin here where the arrow is, then at t equals 0, y is 0. Oops. And what's going to happen is, sometime later y is positive, and then eventually y is 0 again, and then y is negative. This is going to look something like this. The important thing to notice about these graphs, the 0 velocity corresponds to this point on the graph here where the tangent line has 0 slope. Because remember what this is. This is a velocity y direction, which is change in y over change in t. And this is slope of this position graph. You write an equation for this by picking kind of a generic time, t. This red distance here is described by this equation here, this velocity. Your change in y, I'll go ahead and write this out, you get from this area right here. This is a trapezoid. And remember how we do area trapezoids. Left plus right divide by 2 times t. So in this example, that would be 50 meters per second. I'm just going to put NCU for note consistent units. So left plus right, which is described by this equation, a negative 9.8t plus 50. I'll go ahead and just put that in parentheses. Okay, remember, divide by 2. And then times the width, times t. So what we get here is that our change in y, if you work this out, it's going to be 50t minus 4.9t squared. If we put our coordinate system origin here, then at t equals 0, y is 0. So basically the change in y and y are the same. I'm just going to go ahead and get rid of this. So that's pretty much it on projectile motion. I think I've covered really all you need to know to work almost any projectile motion that you are challenged with. You always start by breaking the velocity vector into horizontal and vertical components. Calculate the horizontal and vertical components if you can. If you can't, just leave these as like v sub o cosine theta, v sub o sine theta, and move on. Position graph, or velocity graph, x direction should always be horizontal if you ignore air drag. You'll end up with a linear position graph, an equation that looks something like this. Velocity graph, y direction, will be linear with a slope of 9.8 meters per second down. The only thing that can vary here is sometimes it'll have a positive intercept if young Susie fires the arrow in the air, maybe a 0 intercept if young Susie fires that arrow horizontally, or a negative intercept if Susie fires the arrow in a downward type of direction. This area here, picking kind of a generic t and the velocity that goes with that point, and again, that's y direction. This area gives you the delta y, will always give you an equation that looks something like this. If the initial velocity was 0, this term would be 0. If the initial velocity was downward, this term would be negative. Other than that, nothing else will vary. Once you have these equations for x against time and y against time, now it's just a matter of kind of like answering questions. Tell me a time, I'll tell you a y, or tell me a y, I'll tell you a t. Same thing here, tell me an x, I'll tell you a t, tell me a t, I'll tell you an x. Now the other thing that can happen is you can have problems or questions that just aren't time dependent, like like maybe we know that the arrow hits the ground here at x equals 80 meters and y equals minus 40. No time information, just x's and y's. Well, then what you do is you solve this one for t, plug it into this equation, and you'll have an equation with only x's and y's. I'm not going to do that because the video is kind of at my outer edge here time-wise. So I hope this helps with how to attack projectile motion problems. Have a great day.